Imagine this: billions of years ago, the most massive planet in our solar system wasn't just the giant we know today. It was a true monster. Twice the size, glowing hot, and wrapped in a magnetic field so strong, it could shred anything that got too close. Not science fiction. Real science. And it changes everything we thought we knew about the early solar system. Jupiter, often called the king of the planets, is already massive enough to hold over 1,300 Earths inside. But what if I told you that the Jupiter we see today is just a shadow of its former self? That once upon a time it was so much larger, so much hotter, and so much more powerful, it could have rivaled a young star? Let's go back. Way back. Around 4.5 billion years ago, when the solar system was still forming out of a swirling disk of gas and dust. In this chaos, the seeds of Jupiter began to take shape. As more and more gas fell onto its growing core, Jupiter ballooned into an enormous, fiery world, about twice its current size. And that's not just a random guess. Astronomers today, using both computer simulations and observations of other young planetary systems, believe this inflated Jupiter stage was very real. This early version of Jupiter wasn't a peaceful place. It radiated energy like a miniature sun, its outer layers puffed up from the intense heat of formation. It spun rapidly, faster than today, and generated an internal dynamo that powered an absolutely massive magnetic field. We're talking about a magnetic field hundreds of times stronger than Earth's, and likely even stronger than what Jupiter has today, which is already the strongest of any planet in our solar system. Just for comparison, Earth's magnetic field protects us from solar radiation. Without it, our atmosphere would be stripped away. Now imagine a magnetic field 20 times stronger than Earth's, which is what Jupiter has now. Then double it or more. That's the kind of invisible force we're talking about in early Jupiter's past. It would have carved out a giant bubble in the solar wind, a massive magnetosphere stretching millions of kilometers wide, possibly larger than the orbit of Mercury. This means early Jupiter wasn't just big and hot, it was dangerous. Any object passing near it would have been bombarded with intense radiation. If you sent a spacecraft through that field today, it would fry its electronics in seconds. Now multiply that by 2 or 3. That's what early Jupiter might have been like. A giant engine of radiation and magnetic fury. But why was Jupiter so big in the first place? The answer lies in gas accretion. During planet formation, once a rocky or icy core reaches about 10 Earth masses, it begins to pull in hydrogen and helium gas from the surrounding protoplanetary disk. This gas piles on fast, sometimes in just a few million years. As the gas collapses onto the core, gravitational energy turns into heat, puffing the planet up like a balloon. The result? A gas giant glowing with the energy of its own formation. Over time, that energy leaks away. The planet cools, contracts, and settles into a smaller, denser state. That's what happened to Jupiter. It lost its early heat and with it much of its size. Scientists estimate that young Jupiter may have been twice its current radius, but it wasn't twice the mass. It was just inflated by heat. Think of it like a hot air balloon. As long as the air inside is hot, the balloon stays big. Let it cool and it shrinks. Jupiter cooled slowly over billions of years, eventually becoming the dense, banded world we know today. But the traces of that ancient, massive phase are still there, hidden beneath its thick atmosphere. And there's more. That oversized magnetic field we mentioned earlier? It wasn't just a side effect. It may have played a critical role in shaping the solar system. Jupiter's magnetic field creates powerful radiation belts, so strong that any spacecraft flying too close must be specially shielded. But billions of years ago, that same magnetic field could have cleared out charged particles from a vast region around the young sun, influencing where other planets formed and how much material they could gather. In fact, some scientists believe that early Jupiter's magnetic field may have created a kind of barrier in the solar system. It could have prevented too much icy material from drifting inward, helping to set the boundary between the rocky inner planets, like Earth and Mars, and the gas giants further out. That invisible wall of magnetic force may have shaped the architecture of our entire planetary system. And then there's the question of habitability. Life as we know it needs water, stability, and protection from harmful radiation. Earth is habitable partly because we orbit in a calm region, away from intense radiation belts. But early in the solar system, Jupiter may have been a much more aggressive neighbor. Its powerful magnetic field could have flung radiation into nearby space, possibly sterilizing regions or affecting early planet formation. Some models even suggest that early Jupiter migrated inward, coming closer to the Sun, before moving back out to its current orbit. If true, this temporary Jupiter on the move phase would have disrupted other young planets, possibly ejecting some from the solar system or smashing them into one another. Our solar system might be relatively calm today, but it was likely a cosmic war zone in its early days, and Jupiter was one of the biggest players. This idea of a larger, hotter, and more magnetic Jupiter also changes how we think about gas giants in other systems. Astronomers have discovered many hot Jupiters, giant planets orbiting extremely close to their stars. These worlds are often inflated, just like early Jupiter, and their magnetic fields might be even stronger due to intense stellar interactions. By studying them, we're getting a glimpse into our own past. In fact, missions like NASA's Juno spacecraft, which is currently orbiting Jupiter, are helping scientists probe deep into the planet's interior. Juno has revealed strange features: metallic hydrogen inside the core, a fuzzy, diluted center, and shifting belts of gas influenced by powerful magnetic forces. All these clues point to a planet that was once more extreme, more chaotic, and more dynamic than we ever imagined. Even the shape of Jupiter's magnetic field is unusual. It's not symmetrical. It bulges out in strange directions, unlike Earth's simple dipole shape. This weird structure may be a relic of that ancient, more powerful dynamo, one that churned with even more heat and movement billions of years ago. And here's the big twist: Jupiter's early magnetic power might not be gone. It could still be lurking in the deep interior. As the planet cools further, scientists wonder if new magnetic behaviors could emerge, changing the planet's field again in the far future. All of this paints a picture of Jupiter not as a static gas giant, but as an evolving, living world. A planet that was once twice as big, fiercely magnetic, and glowing with its own heat. A world that may have shaped the destiny of Earth itself, and might still hold secrets that could reshape our understanding of how planets form and live. But we're not done yet. In Part 2 we'll explore even deeper. What happens when we compare Jupiter's ancient past with other massive exoplanets? Could early Jupiter have come close to becoming a star? What would that mean for the rest of the solar system? And how does this knowledge impact our hunt for habitable worlds beyond? Stay tuned, because Jupiter's ancient power might just hold the key to understanding not only our past, but our future in space. But what if Jupiter's history wasn't just about being bigger and more powerful? What if it nearly became something else entirely, a star? That may sound dramatic, but the idea isn't as far-fetched as it seems. When we look at the early solar system, and especially young Jupiter, some scientists believe it came dangerously close to crossing the line between a planet and a failed star, a brown dwarf. The only thing that stopped it was timing and just a little more mass. See, the boundary between a giant gas planet and a brown dwarf is all about mass. Brown dwarfs are objects too small to ignite sustained fusion, but too big to be called ordinary planets. They burn deuterium for a short time, giving off heat like a star in its youth. The line between a massive Jupiter and a brown dwarf is blurry, but the dividing point is about 13 times the mass of Jupiter. Our Jupiter didn't quite make it there. But in its early years, twice the size, super hot, with intense internal pressure, it looked more like a baby star than the gentle giant we see today. Now, imagine what would have happened if Jupiter had gained just a little more mass during formation. A slightly denser gas cloud. A bit more material funneled in. It might have crossed that critical threshold, begun nuclear fusion, and become a brown dwarf. The Sun would then have had a companion. And the solar system? It would have been a binary star system, with one true star and one dim, reddish substellar object shining weakly in the distance. That would have changed everything. The gravitational balance of the solar system would shift. Planet orbits would warp. The asteroid belt, the Kuiper belt, maybe even Earth's orbit, could have been unstable. Life as we know it might never have had a chance to begin. So when we say Jupiter nearly became a star, we're not just playing with sci-fi ideas. We're talking about an alternate path that could have erased our very existence. Even now, when we look at brown dwarfs orbiting other stars, many of them look just like what early Jupiter must have been. Hot, inflated, strongly magnetic, and radiating more heat than they receive. In fact, some young exoplanets have been directly imaged glowing in infrared light just like baby stars. These super Jupiters often orbit young stars, and studying them helps us rewind the clock on our own system. By comparing their size, heat, and magnetic fields, we can reverse engineer what Jupiter used to be like. And speaking of comparisons, Jupiter's magnetic field continues to be one of the biggest mysteries in planetary science. Even now, it generates a field 20,000 times stronger than Earth's. It powers auroras that could engulf our entire planet. But those are just the remnants. The fossil signature of an even more extreme past. Scientists believe that in its earliest phase, Jupiter's internal structure was far more turbulent. It may have had layers of metallic hydrogen swirling in complex patterns. These turbulent zones, rotating at different speeds, likely created a stronger dynamo than what we see today. This ancient dynamo may have been driven not only by rotation and internal motion, but by the rapid cooling of Jupiter's early inflated envelope. As heat escaped into space, deeper material fell inward, releasing even more energy, fueling magnetic generation on a scale we've never witnessed. And while this sounds complex, the effects were real and brutal. Jupiter would have created a magnetic wall so powerful, it could deflect charged particles on a solar system-wide scale. It's possible that this early magnetic environment affected the chemistry of nearby protoplanets, shaping their atmospheres and even what minerals could form on their surfaces. Some scientists are now studying isotopic ratios in meteorites that may show signs of Jupiter's influence. Tiny changes in composition could be fingerprints of powerful magnetic fields or radiation bursts from ancient Jupiter's fury. In other words, pieces of rock floating in space might still carry the scars of Jupiter's early reign. And here's where things get even stranger. Remember how we said Jupiter might have migrated inwards during its early life? This idea, known as the Grand Tack hypothesis, suggests that Jupiter first moved close to the Sun, possibly as close as Mars or even Earth, before being pulled back out by the formation of Saturn. During this migration, Jupiter would have passed through the inner solar system like a wrecking ball. Its massive gravity and magnetic field would have swept through clouds of gas and dust, scattering material and possibly wiping out other young planetary embryos. That single journey, just a few million years long, might have shaped everything. It could explain why Mars is so small, why Earth ended up in the Goldilocks zone, and why the asteroid belt is filled with a mix of rocky and icy bodies. Early Jupiter's magnetic shield could have added yet another layer to this chaos, turning it from a passive traveler into a destructive force field sweeping across the solar nursery. Now zoom out for a moment. Across the galaxy, astronomers are finding more and more gas giants. Some are 3, 5, even 10 times the size of Jupiter. Many of them orbit incredibly close to their stars, hot Jupiters puffed up by heat and tidal forces. These giants often have massive magnetic fields, and they flare up with extreme auroras caused by their parent stars. By observing these distant worlds, we get a window into what Jupiter looked like during its prime. Every exoplanet we observe is a clue, another chance to piece together our own solar history. And let's not forget Jupiter's role in shielding Earth. Even now, it acts like a cosmic vacuum cleaner, deflecting or capturing comets and asteroids that might otherwise strike our planet. Without Jupiter, Earth might have suffered far more frequent mass extinctions. But back in the early days, when Jupiter's magnetosphere was far larger and stronger, this protection might have extended even further. It could have deflected solar flares, cosmic rays, and high-energy particles that threatened the inner solar system. In this way, Jupiter may have both threatened and protected Earth in its early life. A two-faced giant. On one hand, its magnetic strength may have fried regions of space, prevented delicate atmospheres from forming, and wiped out early planetary hopefuls. On the other hand, it may have created a safe zone, a region of relative calm, where Earth could slowly grow, cool, and become habitable. We often think of the Sun as the primary architect of our solar system. But Jupiter's hidden power, especially in its early, oversized form, might have been just as critical. A gas giant that nearly became a star. A planet with a magnetic field so strong, it bent the solar wind. A protector and destroyer, shaper and shield. Today, as the Juno spacecraft continues to study Jupiter, it sends back data that stuns even the experts. Giant cyclones swirling at the poles. A core that may be fuzzy and mixed, unlike anything we expected. Fields of radiation strong enough to damage hardened instruments. And all of it is the calm version. The quiet aftermath of a wild, powerful youth. As we close this journey through time, think about this. Everything we know about Earth, its habitability, its climate, its peaceful orbit, may be a side effect of Jupiter's past. A past filled with heat, force, and magnetic might. And while that era is over, its echoes remain. Trapped in the layers of gas, hidden in ancient rocks, and written across the solar system itself. Jupiter may no longer be twice its size. Its magnetic field may have quieted down. But its influence is eternal. Because in the story of our solar system, Jupiter wasn't just a planet. It was a force of nature. And its legacy is written in the stars.